All right, so now we're going to pick it up where we left off last time. We had started to look at constructing confidence intervals for the population mean, and we saw that there are two basic cases. One of them is that the population standard deviation is known, and the other is that it is not. So we started with this case because it uses the standard normal distribution, which we're already familiar with. The next case, where the population standard deviation is unknown, requires us to introduce a brand new probability distribution. So we'll do this first, and then we'll get to the new probability distribution. Now, if you look at this formula, you'll notice what's going on here. We have X bar, which is our point estimate, or in other words, it's our estimate of the population mean. And we've seen that before in earlier chapters. Sigma over here on the right is the population standard deviation, which we're assuming that we know. And then dividing that by the square root of n, the n is the sample size. Here's the new part, z alpha over 2. Now, first of all, we have to understand what alpha means. Alpha is related to the confidence level at which we're calculating our confidence interval. The z-score that corresponds to that is what z alpha over 2 refers to. So, oh, and by the way, let's not forget that this piece on the right in the box is our margin of error. So in other words, what you're basically doing is saying, let's take our X bar, our best estimate of the population mean, and then both add and subtract our margin of error to give us an interval so that we have a range of values instead of just a single value as we would with just X bar. So what we want to do now is consider this alpha. So basically, in a nutshell, the way this works is that if you're trying to construct a 90% confidence interval, then alpha is 10% or 0.1. If you're trying to construct a 95% confidence interval, alpha is 5% or 0.05. And for a 99% confidence interval, alpha is 1% or 0.01. But more formally, you can see that 1 minus alpha is the so-called coefficient of confidence, or confidence coefficient. When multiplying that by 100, it becomes a percentage. And up here, you can see that alpha is defined to equal something between 0 and 1. So therefore, this is why we can say that when we have a 95% confidence interval, the alpha is equal to 0.05 or 5%. And we'll see in the next course, actually, that this is known as the level of significance. So once we know that we are looking for a 95% confidence interval, the alpha becomes 0.05. And equivalently, for 90%, the alpha is 10% or 0.10. And for 99%, we have an alpha of 1% or 0.01. Now, let's take a look at the normal curve. Let's say we're trying to construct a 95% confidence interval. The alpha is 5%, but it's actually split up equally between the extreme right and left tails of the distribution. So that 5% alpha is actually cut in half to become 2.5% in the right tail and 2.5% in the left tail. So 5% is equally distributed between the left and the right tails, which implies that the rest is in the center. In other words, everything in between has an area of 95%. Because now you can see that 0.025 plus 0.95 plus 0.025 in the left tail have to add up to 1, and they do. So now the question is, where do we find the z-score, or standard normal random variable that corresponds to a right tail of 0.025, or equivalently, a left tail of 0.975? Okay, so I'm going to show you that in the next slide. The value that we're looking for is the value under the standard normal curve, such that 2.5% is to the right and 97.5% is to the left. Okay, now, how do we find this? There's two equivalent ways of doing this. We can go to our standard normal table, which I have right here, and look in the body of the table for 0.975, or the closest thing we can find to it. Now here, it actually is on the table. But sometimes we have to interpolate between two similar values. So that gives us 1.96 as our z-score. Okay, so what does it mean? it means that for 1.96, 2.5% is to the right of that area, 97.5% is below that area. Or you can think of it as saying that the probability that a standard normal random variable is less than or equal to 1.96 is 97.5% or 0.975. Now, what's great about this is that the symmetry of the normal distribution means that we don't have to do this twice. We don't have to have a separate calculation for the positive z-score and the negative z-score, because due to the symmetry of the distribution, they will be the same number, but with a different sign. Okay, so that means in this case, we have plus and minus 1.96 for the z-scores when we're constructing a 95% confidence interval. By the way, I'm going to show you in a second how to do this more quickly on your calculator, but I've constructed a table for you so that you can see what these numbers look like. And because these never change, you might want to think about memorizing them. It might speed things up for you when you're doing calculations and problem sets, etc. Because you'll see this all the time. So there's based on the same reasoning that we just saw. For 90%, where we have 5% in either tail of the distribution, the appropriate z-scores are plus or minus 1.645. And with 99%, we have plus or minus 2.576. So let me show you how you could do this with your calculator. There's a function in here that can do this very quickly and easily. You don't actually need the table. So you're looking at your TI-84, and what you're going to do is go to the second vars menu, which is where normal CDF is found in the first place. The function you want here is INV norm. Now, the reason why it's called that is because it's the inverse of the normal distribution. Now, for this one, let's see, what have we done? This is actually the 99% case. I just realized it's 99% confidence. That means 1% in either tail. Sorry, total 1% split up between the two tails, and then 0.5% is in either tail in this case. Okay, so in other words, here's what we're looking at. So we need a total of 1% split up between the two tails, 0.005, 0.005, leaving 99% in the middle. So the tricky part is the area. When they say area, what they mean is what area is below the point or the z-score that you're looking for. And we say 995 because the right tail only contains 0.005. Now, keep in mind, too, this is the standard normal distribution. So therefore, the mean is 0 and the standard deviation is 1. And if you punch in those numbers, you'll see that it is, in fact, 2.576. Now, it turns out, though, that if you have this CE, the new version, you'll notice that when you get to this point, which is not true on the standard TI-84, there's another option that they've moved in there. And what that does is it say, listen, where do you want us to measure the tail? Okay, now I don't know if you can see that. It says tail. Now I know it's backwards, but it says tail left, center, right. The default is left. So here's what you can do now. If you move that over to right, what that means is that the area of interest is now 0.005. In other words, instead of saying there's 99.5% in the left tail, we're calling it 5% in the 0.05% in the right tail. And if you go down and hit paste, it's the same number. Okay, so if you have this one, you have the option of switching it to the right tail, which means that you'll enter not 995, but 0.005. So 995 in the left tail is equivalent 0.0005. No, sorry, it's so confusing. It's 0.005. I have to be careful with that. 0.5%, not 5%, 0.5% in the right tail. So both of these will give you the same result, 2.576. And that implies that this one is positive 2.576, and this one is negative 2.576. So those are my z-scores if I'm constructing a 99% confidence interval with the standard normal distribution. Now, that took the place of looking this up in the normal table, of course. Here's the 95% confidence interval case. And again, the only challenging part really is what to do about the area. So now for 95%, that implies 5% is split up between the two tails, or 2.5% belongs to either tail. So we have 2.5% here. And of course, the same thing here, leaving 95% in the center. So area-wise, the entire area below this one, the positive z-score, is 0.975. So in the standard TI-84, that's what you'll type in there, and you'll get 196. If you want to, though, switch this to the right mode, if you find that easier, that's going to give you 2.5% in the right tail. And if you double check, you'll see that you'll get 196 in either case. And so that, of course, means that we have two z-scores plus and minus 1.96. And whatever formula we're using, that is what we mean by z alpha over 2. And then finally, for 90% confidence, we're going to have 10% split up between the two tails, which means 5% in either tail, so that 90% is left in the center. Okay, if you're not sure, just double check and make sure that all the sections add up to 1. Okay. So now we can go, and again, if you use left, which is the default, by the way, in this calculator, you have to switch it to right if you want to, or 0.05 is your right tail. Either way, you'll get approximately, not exactly, but approximately 1.645. So that means this is our 1.645, and this is negative 1.645. They have to be the same because of the symmetry of the normal distribution. All right, so here we go. We have a hedge fund with 500 stocks. Now, by the way, I just want to mention here that with these examples, the size of the population is actually not relevant. It mattered a great deal in Chapter 8, but not here. We're being told that the annual rate of return is normal. The population standard deviation is 0.20, although it isn't written maybe as clearly as it could have been. If we're treating this as a population, and it says the standard deviation is 0.20 or 20%, that implies that it's this population standard deviation. And that tells us that we're going to use the standard normal distribution. We also have a sample size of 10. And finally, we have a sample mean of 0.08. So what we're going to do is calculate the confidence intervals for the population mean at 3 different levels. Okay. So now for 90%, we just got through showing that the z-score is 1.645. This is our formula. And so if you notice, since we understand how that z-score works, the rest is just a matter of plugging everything in. And so what you'll see is that you'll get a margin of error of approximately 10.4%. This is our X bar, okay? So by adding and subtracting 10.4% from 8%, your lower limit is this negative 2.4%. The upper limit is 18.4%. So it's a pretty wide range. The reason why it's so wide is because the standard deviation is actually quite high. It's quite a bit higher than the mean. In other applications, it will be much smaller and the interval will be much more narrow. Now, to get the other two, 95 and 99, the only thing you have to change is right here, the z-score. The rest is exactly the same. So for 95%, we're just literally replacing the 1.645 with 196. And as a result, the margin of error actually increases from 10.4 to 12.4%. And because of that, the interval gets a little wider. We have to include more values in order to be more confident. Okay, so that's an important thing to remember. The more confident we want to be, the more values we have to include in our interval. Okay, and that's because the margin of error gets bigger when we allow for more confidence. Okay. And that in turn is because the z-score gets bigger. Okay, so yes, in all three cases, the z-score keeps getting bigger, which increases the size of the margin of error, which in turn widens up the interval. Okay, so once again, see, the only thing that changes here and so we've got all three results. In each case, it's 8% plus and minus the margin of error. And in order to have the highest possible confidence level, we must allow for the widest range of values. Now, here's some good news. The calculator has a shortcut for doing this. Okay, let's find out what it is all about. We're going to do the same three examples again with our calculator. So this time we're going to use the stat menu, which I don't think we've used this before. And we're going to go to the test submenu. Again, I know it's backwards, but you should be able to see that. And when you get there, and by the way, this is the last example. This is the data we had. We'll start with 90%. You're going to choose number 7, the z interval. How do you know that? Because the word interval indicates that it's a confidence interval, and the z reminds us that this is a standard normal case because sigma is known. When you choose it, pick the stats menu unless you have the original data. Like, for example, here with this case of the stocks, unless you actually have the returns to the individual 10 stocks, which you would put in the lists, instead, you're going to use stats. Stats is where you put the summary statistics, meaning the standard deviation, the sample mean, the sample size, and C level, of course, stands for confidence level. So you put those in, and you go down to the bottom, and you hit the calculate button, and you'll see in the window, backwards, at the very top, there's a range of values, and this is what it looks like. Well, that wasn't so painful, was it? Not at all. Okay, but it's important that you understand what the calculator is doing. You know, it's great that the calculator is fast, but we have to know what it's doing. Okay, otherwise we're not learning this material. And also, it'll prevent you from understanding what comes in future chapters in stats decision making if you don't understand what a confidence interval actually is. Now, let's do the same thing for 90. That was 90. Now we're going to move up to 95. So if you notice, the only thing that's different is here. Okay, everything else is the same. And as we saw earlier, the new interval is right here. By the way, if you do use your calculator, it doesn't explicitly tell you what the margin of error is, but you can figure it out. I'll tell you why, because the calculator will tell you what X bar is. So what you can do if you do not know the margin of error, you can take the upper limit and subtract the X bar. So in this case, your margin of error is 0.20396 minus 0.08, which is, let's see, 0.12396. And when we did this on the slide, we rounded it off to 0.124, if you recall. Okay, so with the 95% case, right there, yeah, 0.124. That's our margin of error. So in other words, if you're using the calculator only, and you need to know the margin of error, this is one way you could do it. It's X bar, which is listed on this printout, by the way, and then adding and subtracting the margin of error, so you can reproduce that by taking the upper limit and subtracting X bar. Also, what you could do is take the lower limit and subtract it from 12%. But I think it's easier this way. Now 99%, we just change the C level to 99, and this is what we get. Nice. All right. Now, what about sigma is unknown? So what I'm going to do is open up a special table that we'll be looking at for this new probability distribution. And we're going to need to take a bit of a detour and learn about this new distribution. If sigma is unknown, we're going to use the following formula. And if you notice, there's a couple of changes. The sigma was replaced by S, of course, but the z-score has been replaced by something mysterious, which could be called a t-score or a critical value. And you can see there's alpha over 2, but there's also n minus 1, and the z has been replaced by a t. Now, what is that all about? Well, that has been taken from the so-called t distribution, which sometimes is called the student's t distribution. The t distribution is a very interesting history, unlike the normal, which has been around for centuries. This one was actually created at the beginning of the 20th century by W.S. Gossett, who was working as the head of quality control at the Guinness Brewing Company in Dublin. The purpose of this t distribution is to explain the properties of sample means when the conditions of the central limit theorem do not hold. Okay, remember, with the central limit theorem, if we have samples that are large enough, 30 or above, and or a normal population, then sample means are also normal. What we did not address in that chapter was, what about cases where the underlying distribution may not be normal and the sample size is small? Then we had a problem up until Gossett came along. We said, you know what, here's a distribution I've created which is well suited for those cases. So in other words, if we have small samples taken from a potentially non-normal distribution, we can use the t distribution instead of the z. Now, what is this thing all about? Well, first of all, I have a graph in here somewhere. And what I've done is this is actually not even Excel anymore. I needed something a little more sophisticated. The blue is actually the t distribution. The green is standard normal. And you can kind of see that they're not very different, are they? They have a lot in common. Now, both of these have a mean of 0, if you notice. They're both symmetrical about the mean. and they're both described by bell-shaped curves. So in that sense, they're identical to each other. Here's where they're different. The T has, if you notice, it's not quite as tall. There's less area near the mean. And if you notice, the tails contain slightly more area than with the standard normal. So that means that with the T distribution, you're more likely to get extreme outcomes, meaning very large or very small, and less that are close to the center. Okay, and that's exactly what Gossett was aiming for. He was saying that sample means will behave differently when the samples are small. In other words, they should be more different from each other. The variation should be different, should be higher. So the net effect of all this is that the T distribution has a higher variance and standard deviation than the standard normal. Okay, that's by design, okay, because this is how small samples behave in practice. Now, here's where it gets a little complex. Where are the normal and the T really the most different? Let me sneak this in here. Note the normal distribution is characterized by the mean and standard deviation. All right, we knew that. The T distribution is characterized by a value which we haven't seen yet. It's called the degrees of freedom. And we're not gonna have time to get into this right now, but the degrees of freedom is closely related to the sample size that is used. So we'll need a formula. Every time we see the T distribution, we're going to need a formula for calculating the degrees of freedom, but it's always going to be related to the sample size. And in fact, for this chapter, the degrees of freedom is always going to be equal to n minus 1. That will change in later chapters, but for our purposes in chapter 9, the degrees of freedom is simply another way of saying n minus 1. Okay, so that number is what uniquely characterizes the T distribution. The shape depends on that n minus 1 parameter. Let me show you what I mean. This graph that I just showed you, the T distribution has 5 degrees of freedom. What happens if I increase that to 30? Now remember, 30 is the cutoff point according to the central limit theorem between normal and non-normal behavior. If I increase the degrees of freedom here to 30, oh, now look at that. You almost can't tell them apart. They're so close. Wow. In fact, I'm sure you're having a lot of trouble telling the difference between the two. The blue is ever so slightly more spread out. 30 degrees of freedom. And they're almost identical now. So this is using the T distribution is particularly important when you have small samples. After they get to a certain size, it's not quite as important. In fact, after a certain point, it almost doesn't matter whether we're using the T or the Z. But for small samples, it does matter quite a bit. Okay. Well then, by the way, I want to show you the moments of the T distribution. We always have moments with every new probability distribution. So the mean is 0, just like the standard normal. You can tell by looking at the graph. Now, by the way, I just want to introduce a new symbol here. This is the Greek letter nu. Although when you print it out, the fonts in this PowerPoint make it sometimes difficult to see the difference between nu and v. But nu is a Greek letter, and we use it to represent degrees of freedom. So in these examples, the degrees of freedom is equal to n minus 1. But that will change in later chapters. So the variance of the t distribution is nu over nu minus 2. All right, degrees of freedom over degrees of freedom minus 2. And of course, that implies that the standard deviation is simply the square root of that. Okay, and you can see that here. Now, by the way, this gives me an opportunity to show you why the t distribution is so close to the standard normal when we have a lot of degrees of freedom. Let's just take a look at these calculations. So radical 5/3 is approximately about 1.29. Now you know that the standard normal, this would be 1. 1.29, oh my God, that's almost 30% higher. That's why with 5 degrees of freedom, the curve is spread out the way it is, because the standard deviation rather, is about 30% more than it would be for the standard normal. And that's indicated by the spread. The tails have more areas, the center has less. But if we increase that to 30, consistent here. The square root of 30 over 28 is approximately equal to 1.035. So you can see even still slightly higher, but not much. That's getting pretty close. And clearly, as the degrees of freedom keeps going up, this number will continue to shrink and get closer and closer and closer to 1. So that explains why these two graphs look the way they do. You can see it's almost indistinguishable here between the two, whereas here you can really see the difference. Now, how do you find values under the t distribution? There's a table here, which I will open now. I think I already got it. So on the left-hand side, you see degrees of freedom. On the top, you have tail areas. Okay. So, for example, if you need to find the tail area, that would be something like this. By the way, what's interesting about the t table is that it is showing you the areas in the right tail. So we've got 9 degrees of freedom. We're looking for a tail area of 5%. And in the table, that shows up as 1 point. Oh, sorry, I did not illustrate that correctly. The tail area is the 5%. The t-score, or critical value, is 1.833. According to this table, we find it at the intersection of We call it T95 with 9 degrees of freedom. And this 0.05 is the right tail area. So that's the 1833. Now, had this been the standard normal distribution, I would remind you that with 5% in the right tail, and we saw this earlier tonight, we would have, oh, so what is happening is that for the same critical values, or there's the same alphas, I should say, the t-score will always be higher than the corresponding z-score. So in other words, down here it's 1.645, on top it's 1833. The t-score will always be a little bit more because the curve is spread out more. Now, if you want to avoid using this table altogether, there's a function here corresponding to the INV norm. It's called INVT. Now, here's some bad news for you. If you happen to have one of the older TI-83s, they did not see fit to put this function in there for some reason. It's in the 84 and the 84 CE though. So it's in the same menu as INV norm. So you'll hit second vars, number 4 INVT. Now this time it needs the tail area and the degrees of freedom. So let's reproduce this result. Put 95% for the tail area, meaning this area down here. Actually, let me just double check and make sure they didn't change that on this CE version. No, that's right. Okay. And so if you type that in, what you're seeing here, you will get the 1833. Okay. Now, I noticed that here you don't seem to get the option of turning this into a right tail. Okay, so you should always be ready to do the left tail area. That is much more normal. All right. Now, with all that being said, how do you construct a confidence interval for the t distribution? Well, this is very similar to what we had before, isn't it? Remember, if sigma is known, then you would have x bar plus or minus z alpha over 2 sigma over radical n. So the differences are very subtle. And also this entire expression is still the margin of error. Okay, so let's do one of these. A university has 10,000 students whose GPAs are normally distributed. A sample of 10 students is chosen. The sample mean GPA is 3.10. And the sample standard deviation is 0.25. And we're going to construct a confidence interval using 3 different levels. Of course, 90, 95, and 99. So we've already looked this one up. With 90%, 5% in either tail, we're going to end up with a t-score of 1.833 with 9 degrees of freedom, that is. So you plug everything in, and of course, just calculate what you're seeing in front of you, and you'll get the right answer. So here's your margin of error, whatever that is. You'll add and subtract that from 3.10 to get your confidence interval. Well, if you do the calculations, you'll see that this is approximately equal to 0.1449. So you're going to have 3.10 plus and minus 0.1449. with 90% confidence. And then you just do the calculations, add and subtract, and this is your 90% confidence interval. Oh, I see. Okay, that's not so bad. And now you can guess what's coming next. With 95%, we're only going to choose a different t-score to reflect the fact that there's a higher level of confidence, which means we need to include more values in our confidence interval. This time it turns out to be 2.262. And if you go to your calculator, the degrees of freedom is still 9. Now the area is 2.5% in either tail. Or think of it as everything below this point is 0.975. So if you go to the calculator, INVT, change the area to 0.975, 9 degrees of freedom, and it's 2.262 for your t-score. And then you plug that in, and there you go. And this is the final result. And then finally, for the 99% case, the t-score goes up to 3.25. Okay, which again, you look it up with the INVT function. Plug it in. And once again, the interval gets even wider because we're including, we want to be more confident, we have to include more values. This is the final result. Now, you're probably thinking to yourselves, before we were able to find a calculator function that took care of all of this for us. Is there one for the t distribution? And the answer is yes. Okay, here's what you have to do. Let's use the same example, but we'll go back to 90% and see what we would have done on the calculator with its specialized functions. And if you look at that same menu we had a minute ago, stat tests, instead of choosing number 7 z interval, now we choose a t interval. Why t? Because again, sigma is unknown. So stat, it's the same menu. In fact, it's right below. Z interval is 7, t interval is 8. Make sure you're in the stats mode. And this, by the way, the calculator uses SX. When we use S, it's the same thing. Okay, they're both the sample standard deviation. Okay, and of course, at the end, you have to tell it that we're looking for 90% confidence level. And then you'll type it in and you'll hit enter and you'll say, wait a minute, that's exactly the same that we got with our algebra. And that's, of course, correct. And then to get the other two, literally the only thing you have to change is the C level or confidence level. So you're down here, we just changed this number and you're all set. And it couldn't be much more straightforward, could it? No. And then once again, 99%, we're just changing the C level and we're good. Run it. And this is your result. Okay, so up to this point, our entire discussion was centered on finding confidence intervals for the population mean. It turns out we can do the same thing for population proportions. Okay. Now remember, in this book, we're going to use the letter capital pi to be our population proportion. And lowercase p is our sample proportion. Which can be calculated as x over n, where n is the sample size, and x is the number of elements. Actually, I'm running out of space here. I'll move it down here. X is the number of elements in our sample. With a specified characteristic, let's call it. So let's say, for example, we're studying the proportion of people in the United States who are retired. Okay. So that means the sample proportion would mean you go out and grab a sample of people and find out how many of them are retired. And so obviously, for example, if you choose a sample of 118 of them are retired, that means the sample proportion must be 18% or 0.18. Now, here's an interesting twist. Unlike with the mean, the proportion only follows the normal distribution. We will never use the t-distribution for these cases. That's because what we're doing here really follows the binomial distribution. You recall from an earlier chapter that as we keep increasing the number of trials, the binomial distribution converges to the standard normal. So we can use the standard normal as long as we have a reasonably large number of trials and get a good answer. T will never come into this. All right. And of course, as always, we have a margin of error, which is this entire term on the right-hand side. All right, let's look at a quick example of this. We have a random sample of 105 fast food restaurants, of which 74 of them have at least one vegetarian option, like a salad or something. You don't always see that, do you? No, some of them do. Some of them do not. So that means that X is 74, the sample size is 105. So the sample proportion is 70.48%. So with that information, we want to come up with an estimate of the true population proportion by constructing a confidence interval. How? Okay, well, we're just basically plugging everything into this formula with the understanding that we do need a z-score. But we know how that works already. 90% implies a z-score of 1.645. Okay, and if you forget, you can go to the INV norm function, or you can go consult this little table that I created and say, oh, that's right. Let's see, where is it? This is why I said you might want to memorize this table, or at least write it down somewhere so you can see it. Put it on a little sticky pad on your laptop. Wow, man, that's way, way back here. Here it is. No, here it is. Yes, those are the z-scores for these three confidence levels. And since those are the only three we'll ever use, it's not going to be that difficult to memorize these. Well, you'll see them so often after a while, you'll have them memorized anyway. So it's really no big deal. Anyway, so here we're looking for 90%. I plugged in now the sample proportion was 0.7048. So 1 minus that is 0.2952. Sample size is 105. Here's our z-score. So now we just do the algebra. Here's our margin of error. And you end up with this interval. So what we're saying is that we are looking for the number proportion who have a vegetarian option. Well, we don't know what it is without actually gathering up every fast food restaurant in the entire population. So instead, we have this confidence interval. It's somewhere in this range between 63 and 77.8%. To be 95% confident, We replace the z-score with 1.96 and then plug them in. Yes, there we go. And that, of course, will make the margin of error larger and the interval will be wider. How wide? Well, the new margin of error is 0.0872. And so this is our new interval. And then finally, to be 99% confident, we recall that the z-score there is 2.576. So we replace the others with that. And here's our new margin of error, giving us an even wider interval from 59.02% up to 81.94%. Now, so far, the calculator has rescued us from doing a lot of algebra when we're looking at intervals for the mean, whether they have the t or the z distribution. Is something similar going to happen with proportions? Well, it turns out the answer is yes. Okay, so let's go back to that stat menu. Stat tests, to be specific. Let's find it. Stat tests, yes. So this time, now keep in mind, there's a proportion involved. So what they've done here is they call it one prop z-test, prop standing for proportion. And if you look at the choices, there's only two of them, one prop and two prop. In stats decision making, you'll be doing this with two proportions. Then when you get there, it's only going to ask you for a few things. It's going to, now it's, oh, I just realized, you know what, I only just got this spectacular new TI-84CE during the summer, and I'm still noticing little differences with the TI-84. I don't know what they mean here. They have, oh, I know what happened. I picked the wrong one. Oh, geez. Okay, sorry. False alarm. I was getting concerned here for a second. Yeah, I picked the wrong one. Sorry. Yeah, that doesn't help. Stat tests. Yes, I did, didn't I? It's number one. No, that can't be right. What did I do here? Oh, no. You know what? This is a typo. Oh, crap. This is supposed to be A. Oh, my God. All right. Sorry about that. A prop Z int. Prop for proportion. Z for the standard normal. Int for interval. Confidence interval. All right. I will make a note to myself to fix this. Nothing is more annoying than typos. Okay. Typos are like weeds. You have to keep tearing them out at the roots every time you find them. You can't let them keep growing, that's for sure. Otherwise, you'll never catch them. All right. So when you get there, it's going to ask you just for a few things, X, which is the number in this case of restaurants with the vegetarian option, 74. Then you've got 105, the sample size. And then all you need is the confidence level. Wow, that was easy. They calculate. And yeah. The one thing I do want to point out is that in addition to the interval, it prints out for you this little P with a little pointy thing on it. 0.7048, let's say. This is the sample proportion. We're using plain P for this. They're using P. This is actually P caret, or more informally, P hat, it's sometimes called, because it looks like a little pointy hat. I know, it sounds silly, but that's how it's often referred to. This is our result, okay? And of course, I could easily change my confidence level just by switching C level, and I wouldn't have to change anything else. All right, now there's one more topic here we want to consider in this chapter, And this is something we haven't thought about before, but every problem we've looked at, we were given the sample size, but keep in mind that when we choose samples, it's possible that we have some control over the size of the samples that we can pick. Let's say you're a manufacturer and you are testing whether or not the parts you're making are all of sufficient quality. And so you might wonder, like, how big should my samples be to do this correctly? So that's what this next section is about. Picking the sample size that guarantees that your margin of error won't go above a certain level. Okay, so like, let's say that I'm making potato chips, and I want to make sure that each chip is within 0.001 ounces of the correct value. Well, I can make sure of that, but I'm going to have to find out how big my sample size needs to be. So what I'm going to do is show you the formulas for doing this, which what we're doing is basing at least this one on the standard normal distribution. So what this N represents is the minimum sample size needed to ensure that the margin of error is less than or equal to this E that you see here. So think of that E as our target margin of error. We don't know what it actually is. This is the target. We're hoping, what we're trying to do is say, listen, we don't want E to be above, let's say, 5%. What sample size do I need to guarantee that? Because, as we mentioned before, the margin of error will shrink if the sample size grows. So there's large samples have smaller margins of error. And so we're trying to find the exact point where our sample size is enough to make sure that our margin of error is no more than our target. So let's do, now this is actually a lot simpler than it sounds. It sounds complicated, it's not. This Z, by the way, is our Z score. The book, for whatever reason, leaves out the alpha part. It just calls it Z. So here's what I mean. A retail chain wants to estimate the mean amount that each customer spends in its stores at a 95% level of confidence. The population standard deviation is 10. The margin of error, they would like to keep it at 2 or less. What size sample do I need to make sure that this happens? So look how simple this is. We've got 10 is our population variance. Actually, 10 is the standard deviation, so we square it to turn it into a variance. I'll just remind you up here that sigma is 10. Now, because it's a 95% confidence level, the Z-score is 196, which we've seen before. If you're not sure, you can go look it up in the INV norm function. And then the target E is 2. So if you plug those in, if you notice, you're going to get 96.04, which is clearly not an integer. We can't have 96.04 elements in our sample. So the rule of thumb is always round up if we do not have an integer. So that means we're going to choose a sample size of 97. Because this way, the margin of error will be less than 2. Okay, if we choose 96, the margin of error can still be slightly more than 2. So always up. I know you want to round it down to 96, but not in this case. You want to push it up to be conservative. Now we can do something similar with the population proportion. There's a formula that lets us choose how big should our sample be to keep our margin of error at or below E. And again, it involves the standard normal distribution. Okay, those P's are the sample proportions. So let's look at this case. The same store wants to estimate the proportion of customers that use the chain's own credit card for their purchases at the 90% level of confidence. The sample proportion, it turns out to be 0.25. Margin of error, they want to keep it at 2% or less. And since this is a 90% confidence interval, Z is 1.645. Okay. Which again, if you've forgotten how that works, use the INV norm function. So we plug these in and look what we get. Approximately 1268.45. And again, we're going to round it up and we end up with 1269. Okay. So that wasn't so bad. Although this is not in your calculator, you have to do this yourself. The only thing you can get out of the calculator is for the z-score INV norm. Okay. Other than that, you have to do this one yourself. But all the confidence intervals in this chapter can be done with a built-in function on this calculator. So that definitely takes away some of the burden. But you have to understand what's happening. You have to understand what the confidence interval is telling us and what it means, and under what conditions you use T and under what conditions you use Z. So the calculator is helpful, but it's not meant to be a substitute for understanding. Okay. So anyway, so that means we're done with chapter 9. So what's going to happen is when you come back in September for stats decision making, it's been my experience that not everybody starts at the same location in stats decision making. What I usually do is I start with chapter 10, the next chapter, which is hypothesis testing, after quickly reviewing some of the highlights of this semester. I've been told that other professors will start maybe at 7 or 8 and take it from there. But any way you look at it, this is the dividing line between stats 1 and stats decision making. And so I don't know if I'll see you in September, but if I do, we can review this material very quickly and then go ahead and start chapter 10. If not, you have all these slides that you can review as you need them. And you'll almost certainly not forget any of this, since it's only, 3 weeks until school starts again, something like that. And that's one of the good things about taking this during the summer. It's going to be very fresh in your memory, whereas most of the others haven't thought about this since May, and they're going to be a little of a disadvantage, but with a little reviewing, they'll be fine too. But you definitely have an advantage here that you just got through seeing this material, and so it's fresh in your memories. And so we'll have to stop it right here. Now, I did post all the remaining assignments because it's so late in the semester. Realistically, all we can do now is have the midterm and the final and the one problem set that I already posted, because the course ends in the 7th and I have to have time to correct everything. So what you want to do is get everything in as soon as possible, but just be aware that, you really want everything done by the 7th, because I'll try to be lenient, but I can only wait so long for your work. So if you have a legitimate issue, you can let me know and we can maybe get you an incomplete. But other than that, try to have everything done by the 7th so I can correct them in time and give you your grades without any difficulties. Okay. So I hope you got a lot out of this course, because this is really the foundation of a lot of courses you'll be seeing in Gabelli. And not everybody loves statistics, but I mean, as long as you're able to use it, that's the important thing, to understand it when you see it and know what to do with it. That's really all we can ask for. If you happen to like it too, that's absolutely wonderful. It's like icing on the cake. So anyway, I will wish you a good night. And, of course, as usual, if you need any help with anything, you can send me emails, or maybe we can arrange a Zoom conference session or something. But the new material is done. And so that way you can just focus on your assignments, and then possibly I'll see you again in September. Okay, so good night.